Spiders have thrived for millions of years, evolving into over 50,000 species, each uniquely adapted to its environment. From tiny jumping spiders to massive tarantulas, their remarkable locomotion captivates us. They dart across flat ground, scale steep inclines, or even cling to ceilings with ease. Drawn to this diversity, we noted their leg sizes vary purposefully. Their leg morphology, particularly the varying lengths of femur and tibia segments, is key to this adaptability, inspiring our project's focus. In robotics, navigating diverse terrains with efficiency is a pressing challenge. This drove our team to develop a spider-inspired hexapod robot investigating the following hypothesis. How does leg length ratio affect moving efficiency of a spider-inspired robot on flat and inclined surfaces? To test our hypothesis, we needed a robot with adjustable leg sizes. We chose a 2-link leg hexapod to simplify the design while capturing the essence of the spider's mobility. We engineered this 6-leg robot with adjustable leg segments. For each leg, we were able to adjust the size of the femur and tibia segments to 5 different leg length settings. This allowed us to change the ratios of the links and test our hypothesis. Simulation was used to validate the inverse kinematics algorithm and visualize the reachable workspace of each leg. The 3D point cloud confirms that the leg lengths can reach intended foot positions under different femur and tibia lengths, supporting reliable control and gait planning. The robot's motion begins with single leg control. Each leg is modeled as a 3-degree of freedom robotic arm with 3 joints, allowing full control of foot position in 3D space. An inverse kinematic algorithm converts the target foot coordinates into joint angles, which are then sent to the servo motors for execution. To ensure smooth movement, a cubic Bezier curve is used during the swing phase. To improve stability and heading accuracy, the robot uses IMU-based feedback during walking. Yaw deviation is measured in real time and converted into step ratio adjustments through a PD controller, allowing the robot to maintain its intended heading during both straight walking and turning. Roll and pitch data are also used to calculate vertical offsets of each leg, allowing the robot to level its body when walking on slopes or uneven ground. The robot walks using a tripod gait chosen for its simplicity and high stability. The 6 legs alternate in 2 groups. While one swings, the other supports the body. For straight walking, the swing feet move forward in parallel. For turning, their paths rotate around the robot's center, enabling pivot-like rotation. Step targets are defined in the body frame and transformed to each leg's local coordinates using rotation matrices. A gait state machine handles the switching between tripod groups for smooth, continuous motion. This flowchart summarizes the full control pipeline, from inverse kinematics to feedback control and gate logic. With this full control system in place, we proceeded to experimental testing. All experiments used a fully functional robot platform by recording robot motion. Our primary variables included the leg length ratio and the expand ratio, where we tested 3 leg configurations and varied 3 different expansion ratios. For every combination, we ran 3 trials totaling 27 tests per performance metric. We evaluated performance using 3 key metrics: linear walking speed on flat terrain and a 5-degree incline, pivot turn time for a 90-degree rotation, and average current draw across all servos. Then, we used tracker video analysis software to extract movement data. The robot's colored power buttons served as our tracking point. With auto tracking enabled, we generated position versus time plots. From this, we calculated speed using a linear fit to the most stable motion segment. With this setup, we captured accurate, consistent performance data to evaluate how leg design impacts spider-inspired locomotion. To compare moving efficiency, we created an efficiency rating that looks at the ratio between speed and current to quantify performance per power cost. High speed and low current results in higher efficiency. We represent the data using an interaction plot to show how leg configuration and expand ratio impact speed and current. Based on our results, we found the following conclusions. Femur to tibia length ratio significantly influences hexapod robot performance in speed and energy efficiency. F2T5 at 70% expand ratio achieved the highest walking speed on flat and inclined terrain and fastest 90-degree pivot turns. F5T2 at 70% expand ratio showed the highest energy efficiency with lowest average current draw. 70% expand ratio was the most effective across all leg configurations for flat walking and turning. F2T5's speed mirrors spider leg proportions, validating bio-inspired design principles. Results provide quantitative guidelines for adaptive hexapod robots in applications like search and rescue and planetary exploration.